He knows a lot about the science stuff. Professor Dave explains.
We have discussed noble gas electron configurations and the stability associated with them. It is this stability that dictates the behavior of many elements on the periodic table, whether we examine the noble gases themselves, which are inert because of their stability, as well as elements in the s block and p block, which will lose or gain electrons in such a way so as to attain the electron configuration of the nearest noble gas. But let's see how these principles can apply to other elements on the table, such as elements in the d block, the transition metals. Let's first recall that when listing the electron configurations for transition metals, the period number associated with each row describes the s orbital and the p orbitals for that row, but the d orbitals are one behind in terms of the principal quantum number. So the elements in the first row of the d block will fill up the 4s orbital, but then the 3d orbitals. In the next row, these elements fill up the 5s orbital, but then the 4d orbitals. This is the case because of the Aufbau principle. The 3d orbitals technically belong to the third shell of electrons, but because of their shapes and the average distance from the nucleus, they end up being higher in energy than the 4s orbital, which is spherical and closer to the nucleus relative to the other orbitals of similar energy. This is why the d block occupies this space on the periodic table, after the s block. For the reasons we have just described, transition metals will often lose their outermost s electrons first, rather than their outermost d electrons, because if they lose the s electrons, they will empty the valence shell, which is the shell with the highest n value, and attain what is called a pseudo-noble gas electron configuration. For example, silver has an electron configuration ending in 5s1 4d10. This is because one of the electrons in the 5s orbital will be promoted to a 4d orbital in order to completely fill the d orbitals. Now, even though the 4d orbitals are filled after the 5s orbital according to the Aufbau principle, when a silver atom ionizes, it will actually lose this lone 5s electron first, leaving an electron configuration consisting of the krypton core followed by 4d10. This means the n equals 4 shell has 18 electrons and is completely full. So even though this is not an electron configuration that is equivalent to any noble gas, it still correlates with a high degree of stability for the same reason that noble gas electron configurations are stable, as the valence shell is completely full. We can label this situation, where the outermost shell of an atom contains 18 electrons, as a pseudo-noble gas electron configuration. Again, this is similar to noble gas electron configuration, except that noble gases have 8 electrons in their outermost shell. Pseudo-noble gas electron configuration is a condition that will apply to transition metal ions with electron configurations ending in ns2, np6, nd10, like silver plus or something like zinc 2 plus. And it accounts for many of the common oxidation states of these elements, in the same way that regular noble gas electron configurations can account for the common ions of the elements in the s and p blocks. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.